In Calculus 2, one of the big goals is to find the volume of a 3D solid that you get by rotating a 2D region around a line, called an axis of rotation. There are two main techniques for this, the disk washer method and the shell method. They're both doing the same idea, slicing the solid into tiny pieces, finding the volume of each slice and adding them up with an integral. The difference is the shape of the slices and whether those slices are perpendicular or parallel to the axis of rotation. I'm going to explain this in more detail later. First, just a quick reminder of the disk washer method. Imagine I take a region in the plane and I rotate it around the x-axis. So, rotating a function in the x-axis. If I slice the solid with vertical cuts, meaning perpendicular to the x-axis, um, it will be cutting it perpendicular to the x-axis. Each cross looks like a disc or a washer. It depends. It is a disc if it is solid all the way through, or it is a washer if it has a hole in the middle. So the formula for a disc is the volume equals I times the integration from A to B. So it will be A the start, B the end of f of x squared dx. So the integration is in respect of the x. Why? Because of the rotation we did. We're rotating in respect of x. We're also integrating in respect of x for the disk and washer method. Okay, so now let's have a practice with the washer method just for review. So we have here the function y equals x and the function y equals x squared. We know that the formula for the washer method is that the volume is equal to pi times the integral from a to b of f of x squared minus g of x squared dx. It is dx because we are rotating on the x-axis. So the f of x is the function that is to the left, and we can see in here that the one that is to the left is y equals x, and the one to the right, that is g of x, it would be x squared. We can clearly see that in the graph. So now for the values that we're gonna put for our integral from a to b, that will be at the start, so it'll be 0, and then at the intersection, and the intersection is at 1. So we're gonna have the integral from 0 to 1. Put that in. So let's solve it and plug the values that we already know from our graph. Pi times the integral from 0 to 1 of f of x. And we already said that f of x is the left function. In this case, x. And we have to remember to square it minus the right function, which in this case is x squared. X squared. And we also have to square it, so it'll be dx. If we simplify more, it will be the volume is equal to pi times the integral from 0 to 1 of x squared minus x to the 4th dx. And now we just integrate. So the volume is equal to pi times x to the 3 divided by 3 minus x to the 5th divided by 5 from 0 to 1. And now we just use the fundamental theorem of calculus, which is volume equals pi times 1 to the third over 3 minus 1 to the fifth over 5 minus the entire 0 to the third over 3, which is just 0, minus 0 to the fifth over 5, which again is just 0. And then we have that the volume is 2 pi times 1/3 minus 1/5. And we continue, and we have that 5 over 15, taking the common denominator from 1/3 and 1/5 is 15. So minus 3 over 15. This is equal to, the volume is equal to pi times 2 over 15, which is equal to 2 pi over 15. That's what the volume is if we use the integration in respect with the washer method. The washer method works just fine, but there's another way to do it, the shell method. The shell method thinks about the solid in a different way. Instead of slicing it into flat disk perpendicular to the axis, we slice it into cylindrical shells that are parallel to the axis. Imagine peeling an onion. The solid is made of many thin cylindrical layers. So a key difference to remember is that the disk and washer method slices perpendicular to the axis, and the shells slices parallel to the axis. So we have the same example as before. We have our blue graph being y equals x squared, and our red graph being y equals x. Okay, and I'm going to show the rotation around the x-axis in a 3D model, so you can see it visually. So right now, we're going to rotate y equals x. That's our graph. And then now I'm going to rotate y equals x squared. So there you go. That's the form of the y equals x squared. And you can see that there's a certain space between both the graphs. That's where we're gonna draw our shell. And we're gonna draw it horizontally, which it will be parallel to the x-axis. So let me put that into perspective, and right there. That's our uh, kth cylindrical shell. And you can see that we're drawing it from the left function all the way to the right function, and then we're rotating it as well. But it is parallel to the x-axis. And if we see how do we calculate all the shells? Well, first we need the radius. The radius is going to be from the top all the way to the bottom of the axis. Why is that the radius? Well, let me show it to you visually. We go to the 3D plane, you can see that it forms kind of like a circle, and the radius is going from the top to the axis. So that's what we have in a 2D view. It would be from the top to the axis. It also has a certain thickness. That's what we're going to have the dy or dx part of our integration. And the height is going to be determined by the graphs. So we're going to put the right function, in this case, y equals x squared minus y equals x. And now that's gonna leave us our height. Well, now let's see the shell method on paper. We know from our graph that the intersections happen at x equals 0 and x equals 1. For shells around the x-axis, we use horizontal shells, so we integrate with respect of y. So let me draw our horizontal shell, or parallel, from our x-axis, which is this green drawing right there. A key idea to understand is that shell is written with an S, so we're gonna switch our variable that we're gonna integrate on respect with. So if we're rotating on the x-axis, we're gonna integrate with respect of y, and vice versa. So that's something to keep in mind with. And now our formula is that the volume is equal to 2 pi times the integration from c to d. C to d are some variables that are at the y value. And then our integrand, which is what's inside, is r, and r is equal to the radius. And I already showed in the 3D model that it is the difference from here to the top. So it has a height of y, and you know that the x-axis is equal to y equals 0. So the difference is y minus 0, which is just y. That's going to be our radius. And our height is our second variable, so we have r times h. And h are going to be determined by our functions. So it is the right functions minus the left function. So the right function, which is y equals x squared, minus the left function, which is y equals x. There is something important to keep in mind. We are integrating in respect of y. So we have to write our functions as x equal some sort of y. So how are we going to do this? Is y equals x squared. We take the square root on both sides. Square root of y equals plus or minus x. But since we're on the first quadrant here, we know it has to be only positive. So we're taking only our positive x. And then for y equals x, we just put x equals y. So we have a radius, which is just y. So now the only thing left is to fill up our formula with the values that we have. So the volume is equal to 2 pi times the integral from 0 to 1. You can see at the graph that the intersection point starts at y equals 0 and then y equals 1. So that's why we have our integral from 0 to 1. Our radius, which is just y, times our right function, which is a square root of y, minus our left function, which is y. Then dy, which is our thickness of our shell. Now we just distribute our y. So we're gonna do this and this. So the volume is equal to 2 pi times the interval from 0 to 1 of y 3 over 2 minus y squared dy. After we distribute, we're gonna integrate. So the volume is equal to 2 pi of y 5 over 2, and then we divide by the same number, 5 over 2 minus y to the third divided by 3 from 0 or 1. Now we have one more simplification that we can do, which is the volume is equal to 2 times pi times this 2 goes on top of here, multiplying with the y. So 2 times y, 5 over 2 divided by 5 minus y to the third divided by 3 from 0 to 1. And now we apply our fundamental theorem of calculus. So y equals 2 pi times 2 times 1 to the 5 over 2 power divided by 5 minus 1 to the third minus 3 minus the entire 2 times 0 to the 5 over 2 power divided by 5, which that's just 0, minus 0 to the third divided by 3, which again is just 0. So we can cross this one and cross this one. Now we're left with that the volume is equal to 2 times pi times 2 over 5 minus 1 over 3. And again, we need to take the common factor from both of them. So the volume is equal to 2 pi 6 over 15 minus 5 over 15. And this is equal to 2 pi times 1 over 15, which this is equal to 2 pi divided by 15. And if you can notice, the answer we got from doing the shell method is exactly the same answer we got from doing the washer method, 2 pi divided by 15. So does that mean I can choose to do one or the other? Yes, you can choose. There is an advantage from doing one or the other. So you're gonna ask yourself, when do I pick shells instead of disc? And a good rule of thumb is that shells are usually helpful when the axis of rotation and the way the region is given don't line up nicely. Or if you have to do a lot of very hard algebra to get the washer method to work. So whenever you're stuck on the washer, you go and try the shell method. To summarize, the shell method is just another way to slice a solid, and the 3D graph helps us actually see those shells inside the volume. That's everything for this section.